Good morning, everyone. I am Emma Bullock. I'm in the Department of Mineral Sciences, Division of Meteorites. Been here since January 2006, just as Dick Fisk was retiring, I was arriving. And I'm going to talk to you today a little bit about what I've been calling the solar system's first dust bunnies. So without further ado, and with apologies to George Lucas, a long time ago in a galaxy, actually in our own galaxy, a new solar system was born. It was the collapse of a small part of a huge interstellar cloud of gas and dust that formed our solar system. As this small fragment of the cloud collapsed, it began to spin, and in the center, our new sun formed, and around the outside of our sun, the other material in the disk began to cool, it began to condense, began to form little minerals. Those minerals clumped together to form little dust bunnies, little inclusions. It is those inclusions that I study in order to be able to understand the very beginnings of our solar system. So just to put this in kind of a visual time frame, this is an image from our very own Geology, Gems and Minerals gallery, and it shows the evolution of our solar system. In the very beginning, we have our disk of gas and dust, and as time goes on, material clumps together to form larger and larger objects. Some of those objects are small, they form what we call asteroids, found in the asteroid belt between Mars and Jupiter. Other objects became big enough that they actually underwent melting and differentiation, and they formed planets such as Earth and Mars. But for reference, the material I'm talking about is that very first step on the way to forming planets. So I call them dust bunnies. Their actual proper name is calcium-aluminium-inclusion, or CAI. And yes, I say aluminium, not aluminum. So CAIs, as the name suggests, contain a lot of calcium and a lot of aluminium. These are what we call refractory elements. These are elements that want to be in a solid. They don't want to be hanging out in the gas. They want to form minerals. And so we find our CAIs in meteorites such as this one on the top left, Allende. This is a meteorite that came from an asteroid in the asteroid belt between Mars and Jupiter. So we take our rock of Allende, we slice it open, and we can see on the surface there are lots of these little white objects. Those are our CAIs. And what you can see on this slice is that some of these objects are tiny. Some of the rare ones are quite big, and by quite big I mean about the size of your little fingernail maybe. Some of them are rounded, some of them are very fluffy and irregular, but every one of these objects can tell us a little bit more about the early solar system. And so in the Department of Mineral Sciences, we use a variety of techniques to study our CAIs. I'm sure many of you are familiar with the optical microscope there on the upper left. This uses a beam of light which we pass through or reflect off the surface of a wafer-thin slice of a CAI. We also have a scanning electron microscope, which instead of a beam of light uses a beam of electrons to image our samples and to obtain chemical data. We also have an electron microprobe, which we use to obtain really good quantitative chemical data from our samples. Using the electron microprobe, we can measure elements that are only present in tiny, tiny abundances in our CAIs. And these are examples of the kind of data that we might obtain using those instruments. On the upper left, we have an image from the optical microscope. This is what you see when you polish a CAI thinly enough that the beam of light can pass through the surface of that rock. On the lower left, we have the same inclusion, but this time imaged using the scanning electron microscope. Now, as that beam of electrons hits the surface of the sample, it interacts with the elements that are present in our minerals. Different minerals are made up of different elements and different abundances of elements. And what this results in is those different shades of grey. And you can see just about there's 4 different shades of grey in our CAI. That tells us there's 4 different minerals present. But it's perhaps even easier to see this in the image on the top right. This was again collected using our scanning electron microscope. But this time we took our electron beam and we bounced it across the surface of the sample. And at every point we collected a chemical spectra. And we can take all that chemical data and we can combine it to create these element maps which show us where certain elements are concentrated. And it really clearly highlights what different minerals are there and how they relate to one another. You can very clearly see now there's 4 different colors, that's 4 different minerals. And just in case you don't like pictures and you prefer numbers and data tables, I put one of those in there too. this data table on the lower right shows the chemical makeup of a CAI. And as you can see, it's got a lot of aluminium and a lot of calcium in there. So using the techniques we have available in the Department of Mineral Sciences, we can look at the chemistry, the mineralogy, and the petrology, the texture of our CAIs. But they have so much more to tell us. We have so many more questions we want to ask them. For example, I mentioned that these objects are very old, but exactly how old are they? Well, for that, we have to take our samples to other labs, such as the Ion Probe Lab at the University of Madison in Wisconsin. And I can see I'm running out of time, so I'll just cut to the highlights here. When we talk about how old CAIs are, we're talking about objects that formed 4.567 billion years ago. Imagine that, something smaller than your little fingernail has survived 4.5 billion years. So just to wrap up, I just want to emphasize that our early solar system was an incredibly dynamic place. When we look at our CAIs, we see such an incredible range. We have CAIs that record that first condensation event, and we see that in inclusions such as the one on the left, the fine-grained texture. And this type of inclusion has the oldest age of any CAIs we measure. But we also track evolution of CAIs before they were incorporated into their parent asteroids. This inclusion on the right has undergone melting and recrystallization, and we can see that in its coarser texture and rounded shape. And it has slightly younger age. We can see that CAIs have been melted over a period of about 500,000 years after the first ones formed. So by studying CAIs, we can actually trace the steps that our solar system took on its way to beginning to build planets. With that, I'll end there. Thank you.